our first talk is Beyond Human Reasoning, Bridging the Human-Machine Information Gap. And we have Dr. John Winder, who's the supervisor of the Advanced AI Algorithms section at APL. He serves as the principal investigator of the BHR Research and Development Project, which is developing an AI co-pilot for human-machine teaming in virtual reality. Anika Mistry is a student at Johns Hopkins University, where she is pursuing degrees in both computer science and cognitive science, because one wasn't hard enough. This is Anika's second summer at APL with the XR team, again, because one wasn't hard enough. Last year, she worked on DARPA ACE as a VR developer. That was the project that I was the team lead on, and it was absolutely wonderful to have her here with us working on ACE. And this summer, she joined the Beyond Human Reasoning team as a VR developer, and she's creating VR features to further illustrate AI predictions in air combat. So take it away.
All right, thank you. Yes, so thank you for that nice introduction. I am Dr. John Winder. This is my colleague, Anika Mistry. And I wanted to thank you all for the opportunity and your attention today to tell you about the Beyond Human Reasoning Research and Development project that has been conducted at APL here for the past few years. And the subtitle of the project is Bridging the Human-Machine Information Gap. And really, we're doing that in the context of an AI, an artificial intelligent assistant co-pilot to a human fighter jet pilot. And so we'll talk about all the rationale and reasons behind that and the technology we developed to get us to this point. So I'm sure everyone in the audience is familiar with the increasingly viral, revolutionary applications of artificial intelligence. You probably have heard of things like generative AI, use cases such as ChatGPT, Stable Diffusion, which use a type of machine learning or artificial intelligence called a neural network that's trained on data to generate new data. So in the case of ChatGPT, generating human-like text. In the case of Stable Diffusion and similar models, generating human-like artwork, such as these images that I generated here. And remarkably, those are producible in a matter of seconds. But we've also seen, in parallel, a revolutionary potential of AI as applied to decision-making AI. So maybe some of you are familiar with DeepMind's AlphaGo algorithm in 2016. DeepMind, which is an AI research lab, trained a neural network, AlphaGo, to play the ancient board game Go and actually compete against the top human player. And they also did this with chess and shogi, which is kind of a Japanese form of chess. And were able to defeat the world champion in Go. But this example of revolutionary decision-making AI has also been seen in other use cases. And just as we've seen generative AI kind of take the world by storm, decision-making AI has become similarly powerful. And one example of that is the Alpha Dogfight trials. So in 2020, APL hosted an event called the DARPA Alpha Dogfight Trials, where DARPA had invited 5 different companies, defense contractors, startups, to compete in the training of an artificial intelligent fighter jet pilot. So this was going to be in simulation, an AI that could control a fighter jet and essentially do a dogfight, which is what we call within visual range combat. So these agents were trained in simulation, as I said, and competed against one another. So at the Alpha Dogfight trials, 5 different companies competed against one another. And the best AI agent went against a human fighter pilot, an experienced human fighter pilot. You actually see him up there with a virtual reality headset on, flying against the AI adversary. And he was defeated 0-5. So the AI won 5-0. So that is, again, this was several years ago, and we do believe that this technology will revolutionize the future of warfare, including combat systems and technologies. And we know that on the global stage, other countries out there are not as shy about using AI, and perhaps it's a real likelihood that US pilots, such as our trained fighter pilot up here, will be going up against AI adversaries in the future. And if the AI adversaries have superhuman intelligence in terms of their ability to pilot an aircraft, a fighter jet, how can we help? How can we enable our US operators, our pilots, to come home safely, to survive a fight, and actually defeat an AI adversary? And one of the technologies we're working on is how can we give a human operator, human pilot, AI technology to help them defeat an AI adversary? So how can the human and machine work together to defeat the AI on its own? So that leads to the Beyond Human Reasoning project. This is a research and development project, again, at APL, invested in the past few years, looking at how we can have the best of both humans and machines bring what each other are best at, what the humans excel at. Reasoning, AI excels at computing. How can we give humans the power and precision of machines' decisions at machine speeds? And similarly, how can we have essentially a human go beyond their natural human reasoning? So this is where we get the name beyond human reasoning. And to do this, in that use case I mentioned before, we're working on an AI assistant, in our case, an AI co-pilot. So this is an artificial intelligent assistant to a human fighter pilot. You can kind of think of this like R2-D2 to Luke Skywalker in Star Wars. So Luke flies his starfighter and has R2-D2 droid helping him, basically being a situational aware peer, offering support and helping him automate tasks. In the same way, the Beyond Human Reasoning project has aimed to create an AI assistant akin to that. And we specifically call our AI copilot the Virtual Intelligent Peer Reasoning Copilot. So if you hear Viper Copilot, that is the AI agent that we have trained to help a human pilot. So to give a little bit of background about what a human fighter pilot might need or how an AI could help them, this is a kind of a cartoon of a top-down view where we have two Blue Force fighters. So these are two US operators on the left here facing 6 red adversary. You can think of these as those AI-controlled fighter jets or tangos. These are the different tangos, Tango 1 through Tango 6. You might ask, a typical question you might ask would be, what is posing the greatest threat to our pilots? And just given this picture, you might say, well, perhaps Tango 2, that's at T2 or T1. They're angled towards our pilots, they're closest. But if I add just a little bit more contextual information, such as the tracks of these fighter jets, if you know anything about fighter jets, Tango 1, Tango 2 have just turned, whereas Tango 5 has had a constant bearing. That could indicate that that Tango 5, is the greatest threat because it's had a lock or perhaps a quality track on our pilots for a longer period of time. So that's a simple way in which we just add a little bit of extra information, which a human pilot might have to have a rule of thumb for, or might have to just learn through experience. By adding a little bit of extra information and relaying this quickly to a human pilot, we can help them reason about what the best decision to make is. So beyond that, we also want to have more symbolic representations that we give to the pilot so they can rapidly understand what is going on in the situation around them. We're talking about compressed timelines, highly dynamic, complex scenario that a fighter pilot is operating in. They're under a huge amount of strain, a huge amount of cognitive load. What can we do to represent things succinctly to them? So in this radar plot, we kind of have a symbolic representation of this where threats are represented by the degree of threat by their size. We have circles indicating tracks, engagement quality, preferred shots, so basically which of the AI adversaries is putting our pilot under the greatest threat. Similarly, an AI assistant could compute geometrically reasonable areas, such as a detection zone of these adversaries. What can the AI adversaries detect about our pilot, and compute derived computations such as if those adversaries were to fire a missile, what would be that flyout region? Where is the danger zone? What is the point of no return for our human pilot? And can we recommend in a timely manner our Blue Force pilot, our US pilot, to evade appropriately? So that would be the kind of question, and that is exactly the kind of question that we have been training our AI copilot to detect, learn, and use in an assistive manner to a human pilot. So the Viper copilot, the Virtual Intelligent Peer Reasoning, or Viper copilot, is an AI-based agent that is trained to detect what we like to call the cognitive blind spots of our human pilot. So these are not necessarily visual blind spots, but they could be. But it's more of the cognitive blind spot in the sense of if you or I looked at the same information, we might arrive at different conclusions. We may be off the proverbial same page. So what can we do to have the AI have the full burden of tracking when we are no longer on the same page, when the human pilot is no longer on the same page with what the AI has computed? You can kind of think of this like what we don't want is a backseat driver, where if you imagine like a GPS system, if you have to make a left and you're in the left-hand lane and you have the left turn signal on, you don't need your GPS saying in 500 feet turn left, in 400 feet turn left, in 300 feet turn left. Instead, if you have the signals that indicate you are doing the correct behavior, don't jump in. The AI assistant does not need to jump in. Only when there's a disconnect, that's that human-machine information gap, that is when we want our AI to jump in and say, hey, we think you've missed something critical. You have a blind spot. And that's the kind of thing that could save your life. If you're a pilot and it triggers in the right time frame, that could help you, that could make the difference between you coming home or not. So again, the key point of this slide is just to say we want our Viper copilot to track, has the human pilot, missed something, and relay that to them if they have. So again, to just set the stage before we go into a little bit more depth about the virtual reality component of this project, we do have in simulation a high fidelity, beyond visual range combat scenario where we have high fidelity simulations of our fighter jets flying, in this case, 1 Blue Force pilot flying against 3 red adversaries. So this is a highly overmatched scenario. Our pilot is in mortal peril immediately from the start of this scenario. It's a bad scenario. Typically they train to never get into this, but if it ever happened, what could the human pilot do to get out of this scenario, right? And this is, just for a little bit more context, the red fighters are those AI adversaries we talked about before that have a variety of short-range and long-range missiles, air-to-air missiles, LRAMs and SRAMs, and our pilot has those as well to help defend against these three adversaries. And what our Viper co-pilot is going to do is, again, predict what the human pilot is attempting to do, estimate what the adversaries are doing, predict what is the next greatest threat, and understand, has the pilot made, based on their actions and the predicted actions, have they indicated a disconnect, basically a blind spot, that is worthy of us, of the AI co-pilot, jumping in to say, hey, we think you missed something. Can we do that under these compressed time frames, and can we do that by using visual and audio cues, especially peripheral vision cues, spatial sound audio cues, to tap into the autonomic nervous system of the human pilot as fast as we can to elicit the correct behavioral response to help save their life. So with that, I'm going to pass it over to my colleague, Anika Mistry.
Thank you, Dr. Winder. So essentially, virtual reality allows the human pilot to interact with our AI Viper co-pilot. The human pilot puts on the VR headset and is placed in a simulated high-fidelity aircraft cockpit. Once in the cockpit, the human pilot can use the hands-on throttle and stick, also known as HOTAs, as well as the pedals to fly the aircraft. In addition to being able to fly the aircraft in the VR simulation, the human pilot is also able to interact with our AI's adaptive contextualized predictions. This is done through a head-mounted display, also known as HMD, which follows around the human pilot's head movements. As I mentioned, this visualizes our AI's adaptive contextualized predictions during runtime. Some of these predictions include estimated cognitive blind spots, predicted probabilities, the likeliest next greatest threats, and recommendations for our human pilot from the AI co-pilot. The system structure and data flow for a VR application goes from the HOTAs and the pedals to the simulation, the AI, which transfers information through network packets to the VR application, which is then developed in Unity and is then placed on the VR headset. The first part of the hardware that I will talk about is the hardware that the human pilot specifically interacts with. This includes the HOTAs and the pedals, which the human pilot uses to fly the aircraft in the sim, as well as the VR headset that the human pilot puts on to visualize the simulation. So the HOTAs have trigger buttons that allow the human pilot to produce certain actions in the VR simulation, and the HOTAs are placed on either side of the human pilot when they are seated in the play seat, which is seen in the image in the middle of the screen. In front of the play seat is the operator station, which is where the sim laptop, which is where the simulation and the trained AI agents are stored, as well as the VR machine, which is where all the VR development is done, and is also where individuals who are not the human pilot and who are not wearing the headset can also see what's occurring in the simulation. The headset that we are using for our VR flight simulation is the HTC Vive. One crucial component of the HTC Vive is the fact that it has audio speakers. These audio speakers allows the human pilot to get feedback that allows them to feel like they're actually flying a fighter jet in real time. Additionally, these audio speakers also allows our AI to communicate with the human pilot through audio cues, which uses text-to-speech technology. The next part of the system structure are the simulation and the AI. As previously shown, the simulation and AI are located on the sim laptop, and they contain the trained AI agents, the combat scenarios, the simulation scoring, timing, and physics, as well as the game logic. The simulation and AI then transfers over information through protocol data units, also known as PDUs. These PDUs contain the status of all the game objects. For example, this can include whether an aircraft is dead or alive at any certain time in the simulation, as well as runtime events such as when a weapon was fired. And then this is placed on the VR application, on the VR machine, which is then developed further in Unity. So essentially, at this point, we have an interactive VR simulation that is able to engage with the Viper AI co-pilot. So if you were to put on the VR headset, the HTC Vive, just like the human pilot, you too would be placed in a high-fidelity fighter jet aircraft. You'd be able to interact with features just like fighter jets interact with in their everyday life, such as the radar plot, which is the black square on the left, as well as the FLIR camera, which is a feature that zooms in on other aircrafts, which is located on the right. Additionally, you would be able to interact with our AI co-pilot through audio components and visual components. For the audio components, you would be able to get brief messages that are imperative for you to hear during runtime that use the text-to-speech technology that I mentioned earlier. Additionally, we have visual components that are necessary for both you as the human pilot as well as us as the VR developers. One feature that we use is a running event log, which is essentially a debug log of events that tells us why the AI is making the predictions that it is. In addition to the VR components that we as the VR developers use to help understand what the AI's predictions are, we also have alerts located in the VR simulation from the AI. Some of these alerts are located on the HMD that I briefly mentioned earlier. The HMD is the green circle that has two geographical features located inside of the green circle and inside of the two rectangular outlines. This includes the range and the altitude, which gives the human pilot a sense of where they are in the simulation. In addition to the factors that allows the human pilot to get a geographical sense of where they are in the simulation, we also have the AI alerts that I mentioned. One of these AI alerts includes the blue arrow, which points to what the AI has identified is your closest enemy aircraft. In addition to the AI showing you what your closest enemy aircraft is, you also receive two outlines of where the other aircrafts are in the simulation, which are represented through the blue squares. In addition to these features, the most crucial AI alert is the red arrow, which points to what the AI has determined is your next greatest threat. This is essentially the aircraft that is most likely to kill you at this time in the simulation. This red arrow appears along the circumference of the HMD and is essentially the AI telling you that you should fly in this direction because this aircraft is targeting you. When the aircraft that is the next greatest threat comes into view, a red circle will appear around this aircraft. While in this image you may not be able to actually see this aircraft, this is actually correct because our air combat means that our aircrafts are beyond visual range, which means that they are beyond the horizon. So if you're seated in the fighter jet cockpit, even if you're a real fighter jet pilot, you wouldn't be able to actually see these aircrafts. As the simulation continues, the AI co-pilot will update its predictions depending on what you as the human pilot decide to do. For example, through the progression of the pictures, you can see that the human pilot decided to follow the AI co-pilot's advice and is flying towards the aircraft that is the next greatest threat. And eventually, the aircraft that is the next greatest threat and the closest enemy aircraft are the same exact aircraft and are both located inside the HMD, so the AI co-pilot and you as the human pilot are in sync. In addition to the visual components that are located on the HMD, we also have visual components in the cockpit that I touched on in the previous slide. One of these components is the FLIR camera, which is on the right side of the cockpit. This camera essentially zooms in on other aircrafts as they are flying in the simulation, which is important for the same reasons as the red circle. These aircrafts are beyond visual range, and therefore you won't be able to see them when you're seated in the cockpit. So this allows you to actually see the aircrafts you are up against. In addition to the visual components that I mentioned, we also have audio components. These audio components are said to you as the human pilot when there's a cognitive blind spot. For example, if there's an aircraft that is targeting you that you have not yet seen in the simulation, the AI co-pilot will tell you the words blind spot, indicating that there is a cognitive blind spot. And now I'm going to hand it back to Dr. John Winder to show demonstrations of our AI co-pilot in action.
So I'm going to show a video. Again, this is a video of our AI co-pilot assisting a first-person view of basically one of our developers had the headset on, is going to fly in this. In this scenario, there are going to be two red adversaries about at 12 o'clock, 1 o'clock, and also one more that our developer does not know about, our pilot does not know about. That is about at 8 o'clock. And so that is actually a visual and also a cognitive blind spot in this case. And typically we found without assistance, you as a pilot have about 10 seconds or less to orient in this kind of a situation before you are shot down. So a very compressed timeline, you have to react quickly to survive. And I'm gonna play the video and we're gonna hear the co-pilot, but our developer, our pilot, did not hear it. But we're gonna hear it so we know that it was correctly detecting when he did not have a shot and when he had a blind spot.
No shot. Blind spot.
So rapidly detected he had a blind spot. He fired, but actually shot. If he'll look down there, of course it's beyond visual range, you can't actually see anything. But you look down at that radar plot, and you can see right there was at about 8 o'clock on the radar plot, a little red dot. That was the AI adversary who shot down our pilot. So now with the Viper AI Copilot's assistance, we're now moving to a paradigm where with the human and AI working together, you, as a pilot, can survive a 1-on-3 basically against AI adversaries in a beyond visual range combat. So here, I will play the video, and this time, our pilot will hear the Copilot, and we'll also get those contextual cues, such as the red arrow and the red circle that Anika told you about. So he's putting on the headset right now.
Blind spot.
That red arrow, he looked over, sees the cognitive blind spot, begins to turn to engage. He's going to follow the recommendation here. Establishes a lock on the AI adversary. Fires. And turns back, and notice we don't hear the AI Copilot saying blind spot again, because it remembers that our human pilot
Blind spot.
had those two. And he says blind spot here because he's going to miss this shot. He missed it. He focuses on the third adversary, shoots it, scores kill, goes back, and is able to survive a 1-on-3 against these AI adversaries. So what is under the hood of our Viper Copilot? In terms of AI developments, we're using a form of neural network called a variational autoencoder that's trained in an imitation learning style, basically to follow the best principles of what a human fighter pilot would do. And by imitating what a human would do, this variational autoencoder also learns what's called a latent space, basically a brain or abstracts concepts that are high dimensional that capture different modes of operation. So based on what it observes and tries to imitate of a human pilot, the AI Copilot's variational autoencoder, or VAE, can actually have a good semantic representation of the concepts of combat, and especially surviving the combat. So in our case, the Viper Copilot must use this latent space to decode what the human's trying to do. And we put this into we basically take the latent space of the VAE and do clustering using an algorithm called UMAP to reduce the dimensionality down to basically a 2D map that we can actually observe, and use that to figure out what does the AI predict the human is going to do. So I'll show you how we're able to do that. And using that, it can generate those alerts. So here's an example of this. I'm going to hit play. What we'll see is a simulation in a 3D. It's kind of like pulled back. We'll have one blue and 3 red. That's one of those scenarios. And then over here, this is a UMAP plot. The axes don't really mean anything. Just the relative dimensions show semantic similarity. If I hit play here, we're going to see our pilot actually scored a shot right there, and then gets put into a disadvantaged position, and we actually took away the missiles from the adversaries to see that they essentially will hunt this down. And we're going to see in the latent space of the VAE, the brain of our copilot, an interpretation of moving from a fight regime into a flight regime. And in fact, we can get more specific than that and have this. I'm not showing the simulation, but I will show as new dots are popping onto this UMAP plot, those are interpretations of the real world events. So in the green zone, we're starting with our pilot advantaged. And then you'll eventually see, as a scenario plays, again, it's not being shown, more events occur. Our pilot is moved down into this red area that is our pilot being under threat. And eventually you'll start to see yellow and red dots. Those are when our pilot is within range of an adversary and actually within engagement range of the adversary, which is extremely, and like I said before, that is putting our pilot in mortal peril. So the goal of our AI copilot is to prevent the human pilot from moving from that green zone into that red zone, right? To use those cues to measurably and quantifiably help keep our pilots alive. And so coming down to the close of all of these technologies together, we want to show that these can be done and processed in real time. So what we'll see is the same video that you saw before, but now with the AI's brain basically interpreting new semantic events. Again, we're going to be starting highly disadvantaged.
Blind spot.
So I'll hit play here, have a blind spot initially. Many of the events are being interpreted as being highly disadvantaged. And so recommendations are being generated under the hood based on these predictions. Our pilot follows the recommendations. It's now a 1-on-2 combat. No new recommendations are being generated. Still interpreted as being under threat. Missed that one. And now as we move into this regime, you'll start to see more of those points pop up on the blue, which is kind of neutral mid-combat. Then eventually, it's a little hard to see, but there's a brown area right there that is getting some final things, some final events coming in, basically showing that we have successfully pulled our pilot out of a highly disadvantaged, very dangerous scenario into one that allows them to survive and come home safely. And so just one more video to bring everything together. This is another one where we see our pilot make some recommendations, or our co-pilot make some recommendations to the human pilot, and the human pilot follow those in a dramatic fashion. So it's already turning to engage, just heard blind spot, got that red arrow pop up, turns to engage these other adversaries, sees that yes, they're there, establishes a lock, fires, takes out the AI adversary. There's another one there. Establishes a lock, fires again.
Blind spot.
And here we have one last final recommendation where we wanted to make sure we didn't forget about that other one because the pilot didn't react fast enough. So our co-pilot said, hey, you still have that other one that you really need to pay attention to. And again, altogether, our Viper AI co-pilot is able to assist a human fighter jet pilot to stay alive and win in these highly overmatched scenarios against superhuman AI. So together, combined, we believe that human machines, if we can bridge that information gap, we can help human operators go beyond human reasoning. And so with that, I want to thank my excellent development team, thank my co-presenter, Anika, and the XR Symposium for inviting us to present.
Okay, hello. I really enjoyed that. And I had a question about, usually when I hear this presented, it's presented under the umbrella term of trust when you talk about humans and machines teaming. And I feel like this did provide a substantial definition of what trust means, the overlap between shared decisions and the edge cases where there's not shared understanding, and I appreciated that. This did seem like a great controlled environment where the amount of information is limited. There are a number, I was trying to think of examples while you were talking, but for instance, things that might influence survivability for other reasons, such as the amount of remaining fuel that you have to
Absolutely.
continue operations. I imagine that no matter how mature a model gets, there's always going to be additional information, whether that's, there's weather information that's not part of your model, or fuel information, or something. Something somewhere, a screw is loose. There's always going to be something that's not there. So what do you think, did you gain any understanding from this that helps you better define or focus in on what trust means or what trust should mean when you're never going to have binary 0 or 1, right?
Yes.
You never 100% trust the human, you never 100% trust the AI. Have you learned anything about how to better define what trust means or should mean?
Yeah, thank you for your comments and that excellent question. Yes, trust is critical here, and we believe by establishing with Beyond Human Reasoning a shared understanding. I talked about that proverbial same page. What we have focused on is making sure we do have that measurable, quantifiable same page from which to then define trust metrics, more sophisticated ones than what we have here. And there's that tired old phrase, all models are wrong, but some models are useful. We believe we have laid the foundation here to then layer in greater complexity, such as fuel considerations, which we actually do make here, but weather considerations. And as you said, every model is going to be imperfect somewhat, but can we measure that? Can we assess that? And can we test that and evaluate that? Because at the end of the day, even though we do want the technologies to help our pilots stay alive, nothing like this would be fielded unless we have that degree of trust. So I believe by having these models that are interpretable, that we can actually look at and see, yes, there's some reading into it, but we are working on quantitative ways to measure how do the predictions of the AI align with what the human operator, in our case a pilot, actually believed. So thank you for that question. All right, thank you.